Matrix inverse. This is another operation with matrix. The notation of an inverse of a matrix A is A with a -1 on the right upper right corner of A. So here is A. This is the notation for A inverse. So they look different, but what is A inverse? Here, by the way, do not read this as a power. A to the -1 is not A to the certain power, although it looks like a power. But it's just a name. It's just the way we represent such a function, such a matrix, which is called A inverse. If a matrix has an inverse. So what do we mean by inverse? Suppose B, instead of using A inverse, right? So we don't know yet if A has an inverse. Suppose there's a matrix B. We say B is inverse of A, then we can check two things. If A times B is identity, and B times A is also identity, then we call B the inverse of A. By the way, this A is not just a rectangular matrix. It is a square matrix. It's a very special kind of matrix. It is a square matrix in this topic when we do the inverse. So in order for this square matrix to multiply n and b, so b, we know that the row number of B has to be equal to the column number of A. So in fact, we also have B as a square matrix. So B is also n by n. Yeah. That in that case, A times B, B times A, always possible. And A times B, B times A, not only possible, we require the product to be an identity matrix of n by n. You see these two properties. First, A times B is an identity. Second, B times A is also an identity matrix of n by n. If both conditions are true, then B is called the inverse of A. So here's a given pair of 2 by 2 matrices. So here A is given, B also given. How do we know B is an inverse? Just to check, right? Just check, because if I want to say B is the inverse of A, then we need to know whether A times B is an identity. We need to know whether A times this given B an identity matrix of the same size, 2 by 2. That is something we have to check. And the same B times A, is it an identity of 2 by 2 also? So after we check both AB and BA, if each condition is met, then B is the inverse of A. So here's the specific calculation. I know you can calculate the product of two matrices. So this task is not very easy. A times B, you put A here, you put B there. So A times B, right, in this order. And after we multiply the two matrices, you will see you get an identity matrix. Do you remember how? So we can just assume the product. Suppose we don't know yet if it's identity. Let's assume I have C11, 12. The second row will be 21, 22. Let's see, how do I get 11? So to get C11, I need the first row of A, first column of B, right? The two vectors, and then multiply the corresponding entries. That is 2 times -7 plus 5 times 3, then -14 plus 15, which is 1. So we got C11 as 1. Then C12. C12 is that first row of A, second column of B, we multiply to get C12. So the corresponding entries for the first row of A and second column of B. So we can do, you see, compare 2 times -5 plus 5 times 2. And the answer is -10 plus 10, which is 0. So we got 0 here. So you just continue to multiply the A and B this way. That is the method on how to find entries of the product matrix. So if you continue in this pattern, you will get a 0 for this one as well, but this one you will get a 1. So you see, that's as a result of multiplying them, you discover you get an identity matrix of 2 by 2. So this is true. Yeah, just checked. And similarly, you can multiply B by A. This is the order of, right? BA, because AB and BA, they are different products. So B times A, so now this time B is the first matrix, A is the second matrix. And then you multiply them, you still get an identity. If you actually calculate the product, you will discover that the result is an identity matrix of 2 by 2. So therefore, we just verified the B, the given B is the inverse of A. So we can only claim that B is the inverse of A if B satisfies the two conditions of the definition of inverse. So for small matrices, if we can find, so for A, we can find the inverse, then how do we use it? So let's assume that A times X equals B. That's a linear system we solved many times. Suppose I know inverse of A. If we know inverse of A, then we just multiply, because these two vectors are the same, so I can multiply both sides by A inverse. So because these two vectors are the same, AX equals B, then AX times A inverse is equal to the B times A inverse from the left-hand side. So in that case, then what we have associative property, you see A inverse So we can associate these two together, and X is just the vector. We keep it. And this A inverse B is still A inverse B. We keep it. So what is the A times A inverse? Suppose A has an inverse. Then that would be identity matrix. Identity matrix of the same size. So this identity times X will still be X. So then immediately this becomes, because this is identity, identity times X will be X. So we can put just the X. So we get a representation for solution X. The X is representable in terms of inverse of A. So A inverse times B, that's the solution of the linear system. So you see the linear system can be written equivalently into this form if A is invertible. So it's for that purpose, for the solution of a system, we can make use of the inverse of A to represent solution of the linear system. Okay, now, and X is uniquely determined if A is invertible. So let's look at this A, which is a small matrix. Can we find its inverse? In fact, there is a convenient formula. So this formula is applicable for a 2 by 2 matrix. If you use this formula, you can quickly find inverse of a 2 by 2 matrix. So I'm going to give you this result. So look at this theorem. The theorem has some assumptions and conclusions. The first of all, the theorem assumed a very small matrix, as small as 2 by 2, because it's easy to handle. So we have a very simple formula for this. So ABCD, it is a 2 by 2 matrix. There are four ABCD, 4 entries of a 2 by 2 matrix. If this number, which is diagonal, right, A times D minus B times C, you see that number is actually the product of this diagonal, the entries along this diagonal minus product of the entries from the other diagonal, BC. Yeah, so that's the number we get, right? After do this difference of the products, we get a number. The number is called the determinant of A, of this matrix A. When this number is not zero, that is when determinant of A is not zero, then matrix is invertible and its inverse can be represented by this form. This form is simply to, as you can see from the given A, we can write its inverse. Let's look at. So what is the diagonal, you see? Swapped. AD becomes DA, swapped positions. So originally you get ABCD, but inverse, you swap the diagonal entries. That is D becomes here, A is there. And for the non-diagonal entries, we do a negative. So the B becomes negative B, C becomes negative C, and That's not inverse. So inverse, according to the formula, you have to multiply this matrix by a number, which is scalar, which is a reciprocal of the determinant of A. So the inverse is represented by this matrix. Yeah, that's the conclusion of the theorem. But how do you verify? In order to show this matrix, before we know it's the inverse of A, we can call it B. For example, we want to call it just simply B. Does the matrix B satisfy the two conditions? We just simply multiply the given A by this B. Do I get identity matrix 2 by 2? If I multiply the B, which is this one, B times A, do I get also a 2 by 2 identity matrix? If both are true, then B is the inverse. Yes, we can verify. Simply multiply the two matrices. You will be able to prove that. So it's a straightforward multiplication, right? You simply multiply the matrix by this matrix and then see if you get identity matrix. So using the definition, we can verify it is indeed the inverse of A. With that, so let's look at for a given matrix, can we find the inverse using that theorem? So the inverse will exist if the determinant of A is non-zero. Let's see, what is determinant of A? Determinant of A for this A is 1 times 2. 1 times 2 minus 2 times 3. See, this product minus that product, 2 times 3. So then we get 2 minus 6, which is -4, non-zero. If it's non-zero, then the inverse exists according to the theorem. So not only exists, we can represent the inverse of A by this matrix. The matrix is first determinant of A, so we put a 1 over determinant of A and times a certain matrix. That matrix is we swap the diagonal entries of A. That is, I put, you see, 1, 2 becomes still, they're still on diagonal line, but 2, 1. And then we will, for non-diagonal entries of A, we will change the sign. So this 2 becomes -2, 3 becomes -3. So be very careful when you try to apply the theorem to find the inverse. After you do this, don't forget to multiply it by a scalar. So that after multiplication by a scalar, then this is the inverse of A. So as you can see, when the determinant of A cannot be 0. If it's 0, it's undefined. So we cannot use the theorem to represent the inverse. So inverse for 2 by 2 exists if and only if determinant is non-zero, then your inverse is represented by this by the formula given in the theorem. So here is the inverse for this given A. After we apply the theorem, right, we found determinant is -4. So 1 over -4 is this -1/4. And times this matrix. then each entry times -1/4. That is the scalar multiple of a matrix. So 2 times -1/4. So this first entry times -1/4. Second entry times -1/4. And then the third entry times -1/4. Last entry, 1 times -1/4. So we get this is the inverse matrix. Of a 2 by 2. So as I commented earlier, for a system, linear system, if you're trying to solve a linear system, if you know the A coefficient matrix, its inverse, then immediately you get the solution X, right? So this is AX equals B for any system, AX equals B, after you multiply its inverse from the left-hand side. And then you get an identity matrix, because this becomes identity. Identity times X, you see, will be still X. So the left-hand side becomes X. The right-hand side is A inverse B. So therefore, your solution is simply the product of A inverse and B. That is your solution, X, for the system. So here, from a linear system, okay, we can show that this system is equivalent to this system, although they look different. So this other system is just reviews the solution of the system. So let's see if I have a matrix A, which I can find easily the inverse, then I can find solution of the system very easily. So here is that problem. I think, yes, here is a very specific system with a small matrix A, which is a 2 by 2, and this times a vector. So let's write the system just to see that A specifically is 2, 5, -3, -7, and X is x1, x2, a column vector, and B is 1, 6. So to solve this system, all we need is to use inverse of A times B. Inverse of A, 2, 5, -3, -7, can be found, right? Then we multiply it by B. So that will give you the solution. So let's find the inverse of this 2 by 2 matrix. So for the given A, its inverse according to that theorem, 2 by 2 is inverse. Let's be careful. I think, yes, let's see what is the inverse. So this A, 2, 5, -3, -7. So this is A. What's the inverse? The inverse will be if we swap the diagonal entries, -3 and 2 now. And then if we do negative of each non-diagonal entry, -5 and +3. So don't forget this scalar. It is 1 over determinant of A. What is the determinant of A? determinant of A, or this A, is 2 times -7, right? It's a -14 minus -3 times 5. It's a -15. So -14 plus 15, that's 1. Determinant is 1. So therefore, 1, that's a non-zero value. So this inverse of A exists, 1 over 1, which is determinant. So therefore, inverse is simply this matrix, because this is simply 1. So we found A inverse. Use that inverse, then we can show that the X, which is the solution vector of the system, is A inverse times B. After we multiply the A inverse by B, we get this. So that means x1 is -37, x2 is 15. So in this example, you see that we have another way to solve a linear system. In addition to the row reduction to solve a linear system, we can also use inverse of A if the inverse of the matrix exists. But it's not always the case. And for any matrix A, the A inverse is not does not exist for every matrix A. So this, if A inverse exists, then we have a unique solution. That means, you see, when you do not have a unique solution, that implies the A inverse does not exist. So this gives us some insight. If A inverse exists, we have only a unique solution. So actually later we will show that it's a necessary and sufficient condition. That means unique solution also implying the A inverse being existence of that. If so, we will talk in more detail about the properties of inverse. So that is on a very small matrix, which is 2 by 2. Then we have some quick understanding of inverse and how to use it to find a solution, a unique solution of a linear system. This process can be extended to this ideas of inverse for solution of a system is still true for a general system. And by n, as long as the inverse exists, we can simply represent the solution. So, but how do we find inverse of a larger matrix? If the inverse exists, that implies the system AX equals B has a unique solution. But finding inverse of a larger system can be more work. So we will, I will talk about that in a separate video.